In 2012, the ATLAS and CMS collaborations observed a particle with a mass of roughly 125.1 gigaelectron volts. The discovery of the Higgs boson confirmed the mechanism of electroweak symmetry breaking and provided the final missing piece of the standard model particle content. However, detecting the particle is only the first step. Precise measurement of the Higgs boson's properties, particularly how it couples to other particles, is required to test the strict mathematical consistency of the standard model and to probe for physics beyond it. One major theoretical avenue is the Higgs portal. Because the Higgs field can couple to hidden sector fields through renormalizable interactions, it provides a highly structured mathematical bridge between visible matter and the dark sector. This side-by-side comparison shows the standard model Higgs potential on the left and the extended Higgs portal potential on the right. The critical addition is the coupling term, lambda phi h. This term dictates how the Higgs field interacts with a stellar field from the dark sector. If that hidden scalar field is protected by symmetry, it becomes a viable dark matter candidate. The math indicates that feebly interacting scalars could be directly produced in high-energy colliders through this precise coupling mechanism. But capturing these rare decay channels presents a severe instrumentation problem. Because dark matter particles leave no direct tracks, their presence can only be inferred by calculating missing transverse momentum across the entire detector array with exceptional precision. These precision requirements strain the limits of existing hardware. In this cross-section of a current-generation macroscopic detector, you can see the dense layers of traditional calorimeters relying on scintillating crystals or liquid noble gases. These legacy materials face physical engineering limitations. They force a hard trade-off. Optimizing for light yield typically degrades timing resolution, and materials with high sensitivity often lack the radiation hardness necessary to survive in a high luminosity environment. Testing the Higgs portal requires timing resolutions of around 100 picoseconds and energy resolutions nearing 1%. Reaching these thresholds requires abandoning macroscopic crystal constraints and engineering a new class of calorimetry from the nanoscale up, utilizing quantum dots. The proposed architecture relies on a highly specialized semiconductor stack, self-assembled indium arsenide quantum dots embedded uniformly within a gallium arsenide bulk matrix. An ionizing particle traverses the semiconductor matrix, depositing energy and leaving isolated electron-hole pairs. Within picoseconds, these carriers are rapidly captured by the quantum dots, acting as localized potential wells. Inside, electrons and holes recombine, emitting precise photons around 1.1 electron volts. This process is extremely fast. By localizing the interaction, the matrix achieves a rise time of roughly 100 picoseconds. The structure generates a massive light yield of 10,000 electrons per mega electron volt, while maintaining a low photon self-absorption coefficient of 1 inverse centimeter. By spatially decoupling the charge capture mechanism from the bulk matrix, this architecture bypasses the slow scintillation decay times limiting traditional crystals. To function in a collider, these nanoscale interactions must be aggregated. The quantum dots are optimized, then arranged into a functional layer 20 micrometers thick. This cross-section illustrates a scintillator module. The indium arsenide layer rests on a rigid substrate. Directly beneath sits an integrated photodiode, detecting emitted photons immediately. These individual modules are stacked vertically, forming a dense calorimetry block capable of capturing cascading subatomic showers. This stacked design enables chromatic calorimetry. Because quantum dots have size-tunable optical properties, their emission profiles are deliberately engineered. By embedding different sized dots in different layers, each depth level emits a distinctly different wavelength of light when struck. Chromatic calorimetry encodes depth directly into the photon's wavelength, turning an optical signal into a three-dimensional map of the particle shower. Capturing this topology generates an immense volume of data. With nanosecond decay times and extreme collision rates, standard readout electronics would create a processing bottleneck. To capture the signal accurately, modules utilize time-to-digital converters. These assign sub-nanosecond timestamps to arriving photons, maintaining the strict timing fidelity generated by quantum dots. This network topology maps how the data flows. Instead of routing raw signals to a central server, The time-stamped data from the calorimeter modules is distributed directly to highly localized IoT edge processing nodes. These edge nodes run specialized deep neural networks. They perform real-time signal processing, classifying Higgs events and stripping away noise before data leaves the module. Recurrent neural networks operate in parallel, actively correcting for systematic timing drift and automatically calibrating energy reconstruction on device. Simultaneously, unsupervised learning algorithms monitor the feed for anomaly detection. Any unclassified, highly unusual events are flagged instantly as potential indicators of new physics. Migrating machine learning directly to the IoT edge delivers the low-latency event reconstruction necessary to operate in high-luminosity collider environments. The viability of this architecture rests on mathematical proof across two specific hardware metrics: timing resolution and energy resolution. This equation defines timing resolution. It calculates the square root of the sum of the squares for rise time, decay time, and electronics jitter. Due to the rapid carrier capture, the rise time variable sits heavily at 100 picoseconds. Sustaining a total timing resolution of 100 picoseconds allows physicists to measure exact time of flight, which is critical for rejecting background pileup in dense particle collisions. The second metric, energy resolution, is dictated by the statistical fluctuations in the total number of detected photons. This graph plots the energy resolution formula. The overall resolution depends heavily on the stochastic term, alpha, divided by the square root of the energy, combined with a constant term. Because the quantum dot scintillator produces 10,000 electrons per mega-electron volt, this massive yield mathematically forces the stochastic term down to roughly 1%. These calculated resolutions prove that the quantum dot architecture matches or exceeds the rigorous accuracy demands of the next decade of particle physics. Applying these mathematical capabilities to actual physics observables begins with direct detection, specifically through the diphoton decay channel, where a Higgs boson decays into two gamma-ray photons. This kinematic diagram outlines the diphoton decay. Reconstructing the Higgs boson's invariant mass requires capturing both photons' distinct energies and their opening angle. These measurements plug directly into this reconstruction equation. The calorimeter's combined precision dictates the final calculation's accuracy. The projected outcome for this architecture yields a diphoton invariant mass resolution of 1.5 giga-electron volts, calculated against a Higgs mass of 125 giga-electron volts. In the 4-lepton decay channel, the advantage shifts to the hardware's 100 picosecond timing, which actively filters out backgrounds from misidentified, slower-moving tracks. These hardware resolutions yield the raw precision necessary to rigorously test the couplings, width, and mass generation mechanisms built into the standard model. But the architecture's true test lies in the indirect search strategy. If dark matter particles are produced via the Higgs portal, they will not interact with the detector matrix at all. They will simply escape unseen. This vector diagram illustrates how that invisible decay is traced. By measuring the trajectories and energies of every visible particle, physicists can map the imbalance in the transverse plane, identifying a distinct missing transverse momentum vector. Confidently isolating that missing momentum requires a background rejection factor greater than 100, a threshold achievable here strictly because of the fast timing response of the quantum dots. This data table summarizes the projected outcomes. With a missing transverse momentum resolution of 10 giga-electron volts, the architecture provides sensitivity to Higgs portal dark matter models, with couplings down to 10 to the negative 4. Returning to the macroscopic scale of the accelerator tunnel, the engineering reality becomes clear. Mapping the dark sector and isolating rare decays requires translating theoretical mathematics into a tangible computing and material science problem. The convergence of nanoscale optoelectronics, chromatic depth mapping, and edge machine learning provides a rigorous, scalable framework to execute the next generation of fundamental physics discovery.